All right, so again, I'm going to be trying a couple of new things here as we get used to this, but I wanted to, so my neck's starting to hurt from looking down at the camera, so I've changed the position of the camera here a little bit. So let's go ahead and start to talk about how a inductor reacts to a sinusoidal waveform, okay? And we're going to talk about this from the concept of the inductive reactance, or what you guys will now know of as X of L, all right? And this is really important because the X of L will determine what the circuit resistance is to an AC signal, which will be based off of two factors. It will be based off of the size of the inductor and the frequency. Sorry, this is too uncomfortable. All right, so let's go ahead and see what we have here. So inductive reactance, or what you'll know as X of L, is the opposition to the sinusoidal current flow of an inductor. Remember that an AC waveform is going to come up, it's going to peak, come down, it's going to peak on the negative, and then come back to zero. Okay, and how is this going to interact with this? Okay, now if you recall, a capacitive reactance is the opposition to the sinusoidal flow for a capacitor. Now what we're talking about is the opposite, because inductors and capacitors are often opposites of each other. Okay, and so inductive reactance is expressed in ohms, just like capacitive reactance is. Okay, and the value of X of L is directly proportional to the size of the inductor and the frequency. What does that mean? X of C is going to get higher. X of L, inductive reactance, is going to get higher as the frequency increases or the size of the inductor gets larger. In lab, we're going to see how both of these operate. Okay, we'll do one where we change the size of the inductor, and then we will also see what happens when we have the same size inductor, but we increase the size of we increase the frequency. Okay, so here's what is happening. Here is our formula. Okay, and this is a formula we're going to be using for the next, oh boy, 4 or 5 weeks at least. X of L. Okay, so go ahead and write that one down somewhere. You'll definitely need it for the lab. Okay, and the formula is 2 pi FL. Okay, now let's talk real quick about why an inductor reacts this way to AC. Okay, so here's what's happening. All right, when the AC is coming up, the magnetic field builds, and it's fighting that current the way that it builds. Then when it starts to go into the downturn from 90 to 180, that magnetic field collapses, again inducing a voltage to go with it. Okay, in this constant expansion and contraction, actually what's happening is it is expanding, collapsing, flipping, expanding, collapsing, flipping, expanding, collapsing, flipping, expanding, collapsing, over and over again. My fingers being the magnetic field. And so this is happening, well, if we're at a 60 hertz, it's happening 60 times a second. Okay, if we're at 10,000 hertz, like we will be in the lab, that's happening 10,000 times a second. Those numbers and that action is very hard to retain in our heads or to even imagine. So doing this is very, very cool. And it's that constant fighting the change in current that creates this inductive reactance that says, hey, no. And it makes it kind of act a little bit like resistance, okay, or what we refer to as inductive reactance. Okay, so the value of the inductive reactance in the waveform, as the value of the inductance or the waveform applied to the AC circuit increases, so does the opposition to the flow of current. Okay, all right, because if X of L goes up, your current goes down. All right, this here is your new Ohm's law. All right, so let me show you here. New Ohm's law here is volts I over X of L. Let me make that a little bit bigger so you can see it. Volts, amps, X of L. Okay? And now to get X of L, you have to know some things. Well, it's going to be 2 pi frequency and inductance in henries. Okay? So this would be the first step in figuring these out. Okay? And this is how we calculate out that X of L when these values are known, when the frequency is known and when the inductance is known. Okay? So let's do a couple of these and let's see how it goes. All right, I think this should be pretty fun. Take this over here. All right, so we will, let's take a look at this and see what happens. I'll come over to my whiteboard. That might have been a little dorky, but we'll do it anyway. All right, so let's find X of L if we have a 5 millihenry inductor at 1,000. So to calculate this out, this would be 2 times pi times 1,000 times 5 millihenries, which is 0.005. Okay? All right, so let's go ahead and bring this up in our calculator and we will run the numbers here. You can go ahead and jump ahead if you want, but we have 2 times pi times 1,000 times 0.005, which is going to equal, I came up with, assuming that I calculated it all right, I came up with 31.4 ohms. Okay, notice that that is in ohms now. All right, so let's run that one more time just to make sure I calculated that out right. Okay, we have 1 times 1,000 times 0.12, 2 zeros, that's 0.5 millihenries. Boom, 34 ohms. Okay, very cool. Very, very cool. Now, let's go ahead and look at this one. These numbers are going to be a little bit bigger. Okay, so we're going to take 2 times pi times, in this case, 10,000 times 1 millihenry, or 0.1 Henry, okay? Because that's 100 millihenry. 1, 2, 3, okay? So 0.1 millihenry. And what does that equal? Let's go ahead and type this in. 2 times pi times 10,000 times 0.1 equals 6,283, and we'll just say 0.2 ohms. All right. All right, very cool. Very cool. This is how we calculate out X of L when these variables are known. Okay, so we'll go ahead and minimize this for now. Minimize this. All right, let's go ahead and get back to the lecture then. So, we can manipulate this equation, all right, if we want a specific X of L. And so what that means is we would be trying to get a set amount of current. So if I know how much current I need, I can calculate out what my X of L needs to be. Okay? And to do that, I could just manipulate this formula right here. Okay? And so let me go ahead and my new formula is F equals X of L divided by 2 pi L, okay? And so when we have this here, this would be our new formula, and let's go ahead and give it a shot. All right, so we have two options here. So, what is the frequency? What frequency will cause 33 millihenries inductance to present the reactance of 2,000 ohms? So I'm going to take 2,000 divided by 2 pi L. Okay, so let's go ahead and type this into the calculator here. And every calculator will be different, but I'm just using the one on the Mac, and it's going to be all right. So 2, I'm going to say divided by, clear, 2,000 divided by, parentheses, 2 times pi times 0.033, close off my parentheses, hit equals. All right, so I'm going to need about 9,645, let's do 0.8 ohms. Okay, that's pretty good, I think. I think that's that's right around where we would expect, and so I think we're good. All right, let's go ahead and do another. Let's go ahead and give another one a shot. All right. So, what frequency will cause a 68 millihenry inductor to present the reactance of 5,000 ohms? Okay. So my formula here is going to be 5,000 over 2 pi times 0.068. All right, so again, I'll go ahead and type this into my calculator here. So this would be 5,000 divided by, closed parentheses, 2 times pi times 0.068. I'm going to hit equals here, and I'm getting about, we'll just go ahead and round up to about 11,703. Oops, ran out of space. We'll call that ohms. All right? And that's how we calculate out a needed inductive reactance, okay, when my frequency can be varied. All right, and this would then give me a set amount of current based off of whatever voltage I might be looking for. Okay, so likewise, by manipulating your X of L, you can determine what inductance you need, what size inductor you need, by basically just swapping out the F and the L. Okay, and so the formula for this is pretty straightforward. Get a new clean piece of paper here. All right. L equals XL over 2 pi frequency. Okay? 2 pi frequency. So this is our formula here. So let's go ahead and run through. All right, so what value inductor is needed to provide a reactance of, oh boy, really specific, 62.8 ohms at a frequency of 1,000. Okay, so again, here's my how I'd write this out: 62.8 over L equals, of course, 2 pi, and I know my frequency to be 1,000 ohms, or 1,000 hertz, sorry. So let's go ahead and type this into the calculator. So 6.28, 62.8 divided by, close my parentheses, 2 divided by pi times 1,000, close my parentheses up. It's saying here that my inductor value needs to be about 0.0, we'll just round up, 1 Henry, or 10 millihenry. Okay? Now, if I want to verify this, I can just run this 2 pi FL, and I would see if I get 62.8. Let's go ahead and do that just to verify. Since I don't have you guys here checking me like I usually do, this will just take a quick second. Look at that. Perfect. We're right on top of that. 62.8. Very cool. All right. I wish you guys were here to correct me when I make dumb mistakes, because I'm sure I'm making some of them. But feel free to send me an email if you'd like. All right. Or a voice message or whatever. Okay. So let's go ahead and run this last one. Okay. So what value inductance is needed to provide a reactance of 2,000 hertz? Okay, or 2,000 ohms, okay? So we take 2 pi over, oh boy, omega, okay? So that's going to be 6 zeros, okay? So what the heck size inductor are we going to do with at that frequency right there to get 2,000? So let's go ahead and clear this out. So we'll take 2,000 divided by, I'm going to close up my parentheses, 2 times pi times 6 zeros. All right. I'm going to close up my parentheses, and I'm going to hit equals. All right. Now, that gives me 0.32 millihenries, or if I wanted to be more specific, 318 microhenries. Now again, if I wanted to verify that, I could run that through this formula right here. Okay? And this is how we can calculate out when we know what resistance we need. Okay? That's how we do this. So now what we're going to do, let's go ahead and come back over to here. So, voltage versus current relationship in a purely inductive circuit, okay? In an inductive circuit, current cannot change instantaneously. Voltage does change instantaneously, okay? Consequently, the voltage leads the current by 90 degrees. Okay, and I think you probably know where I'm going with this if you've been in my classes, okay? We are going to Eli the Iceman! Dun, 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 dun. So, all right, so Eli the Iceman, okay? Now here with Eli the Iceman, what we have is a scenario where we've already talked about the capacitance, but it was represented by the C. Well, the inductor here is represented with the L, okay? So in a circuit with an inductor, in this case, a purely inductive circuit, okay, your voltage is going to lead your current, okay? And it's going to do this by 90 degrees, all right? Which you can see here. Okay, here's my applied voltage. I'm 90 degrees ahead of where my current is. All right, so this is at 90 degrees. This is at 0. And again, this is for a purely inductive circuit. If you throw a resistor in there, you throw a capacitor in there, everything gets thrown off, okay? Everything gets thrown off, so that's not going to work, all right? So for our cases right now, we are at 90 degrees, okay? So here it is, Eli the Iceman. All right, so when we have a purely inductive circuit and a sinusoidal waveform is being applied to it, my voltage is going to lead my current by 90 degrees, okay? But if I have a purely capacitive circuit with the sinusoidal waveform applied to it, okay, you can see here that my voltage is lagging 90 degrees. All right, and they can show this a couple of different ways, and it doesn't matter what point on the sinusoidal waveform you will see that, but you can see that here, okay? All right, and so this Eli the Iceman is something I always remember, okay, because I don't think about this stuff all the time, but when I'm trying to figure out is it more inductive or more capacitive, which will be very, very important in a couple of weeks when we start combining capacitors, inductors, and resistors in a circuit. Okay, we want to make sure that we remember Eli the Iceman. Okay, so now what happens when we have total reactance, when we want to know when we have multiple inductors in series, what happens with the inductive reactance? Okay, well, and I'm going to run through a couple of these examples here for you in a minute. All right, but for the total reactance, if it's in series, we simply add them up, okay? All reactants have the same amount of current. Voltage across each one is the same, okay? And voltage across each reactance equals, voltage across each reactance equals the current times the reactance, okay? So we would use this formula to calculate that out, all right? So let's say my X of L here is 2,000 ohms. Let's say this is 1,500 ohms. This is my X of L for 2, X of L for 1. Okay? So I would just simply, to get my X of L total, that would equal 3,500 ohms. All right, now if I came in here and let's say I added another one, okay, I could come in here and I would say, let's just say this one's 1,000 ohms. My new X of L would be 4,500. Now my current here would just be, my I total would equal, there's a couple of ways to do this, it would equal voltage total divided by X of L total, all right? Or I could take the voltage drop across each one of any of these individual ones and divide it by that value, okay? All right. Now, in a parallel circuit, let me go ahead and pull that up, and we would be using the reciprocal method as well. Sorry, I'm starting to wear myself out here. So here, let's say this one had a value of 2,000 ohms. Sure you can see that, sorry. This one has a value of 1,000 ohms. I could just use my reciprocal method to get my X of L total. So let me show you how we would do that here. We will go ahead, bring up the calculator, clear this out. So we would take 2,000 inversed plus 1,000 inversed equals, take the reciprocal of that, and boom, I'm at 66.7 ohms total. Okay? All right. And then if we wanted to find the individual currents, we could just take the voltage, which again in a parallel circuit, voltage is the voltage is the voltage, and we would divide that by the resistance, okay, or the inductive reactance, and we would find the individual currents there. Okay? So inductance versus inductive reactance. The symbols is L where for inductance. For reactance, it's X of L. The units are henries. For inductive reactance, it's ohms. Okay, this becomes your new resistor in Ohm's law if it's a purely inductive circuit. The values depend on the construction for the inductance. We've talked about that, and you learned it in fundamentals, I know. And the values of L for inductive reactance, it is dependent on the value of L and the frequency. And you will see how both of these affect that, right? You'll see how both of those affect that in our lab. Okay? Now let's look at inductive reactance versus resistance. The symbol is XL. Okay? For resistance, it's R. Both units use ohms. The value for your inductive reactance increases with increase in frequency. For resistors, it doesn't matter what frequency you pump through there. They are a passive component. If you have a 250 ohm resistor, it is just a 250 ohm resistor. All right? For inductive reactance, current lags the voltage by 90 degrees, or you could say that voltage leads by 90 degrees. Okay? In a resistor, and this will become very important next week, your current and your voltage are in phase at 0. Okay? All right. Very cool. Whew. All right, let's wrap this up with a little talk about inductance power. We've already talked about this in our class, so if this is new to you, this will be a little bit of this could be a little overwhelming, but for us some of us already know this from the capacitive reactance conversations. So there are 3 power values associated with an inductor. Okay, we have the resistance power. This is dissipated by the winding resistance and is measured in watts. And this is typically, hopefully, very, very low. Remember that an inductor is nothing more than a wire wound up. So you would hope that the resistance of that wire is super duper low. But we'll measure that in our lab in the next lab. So you'll be able to see how low that actually is. Okay, next week when we talk about this, we will not necessarily be worried about the resistance winding. We'll be more concerned with the actual resistor in the RL circuits. Okay? Then we have the reactive power. This is the energy stored and released in the magnetic field of the inductor. It's measured in volt amp reactance, or VAR. All right, or sometimes known here as PX and PR. All right? And then we have apparent power. For lack of a better term, this is our total power, but we don't use PT here, okay? We just call this apparent power, or PAPP, all right? This is the combination of resistance and reactive power, and this is measured in volt amps, and this is what all your transformers are measured in. When you're sizing out a house, okay, you're actually using volt amps, not wattage, all right? And these will become used in all of our labs as we go through when we get to the RL circuits. All right. And so again, some books will use different markings for this. Sometimes it's PS, you'll see PT, things like that. There will be a difference. So make sure whatever symbol they're using to represent the power that's lost in the resistance windings of the wire, the power that is stored in the magnetic field, or the actual total power, okay? So here's a fun way to think about it, okay? So here, your bartender, me, gives you a brew. This is a very, very popular picture. It's out there a ton. So we see, here's our real power, our kilowatts, okay? All right? This is our reactive power, and this is the total, all right? So in this case, this is our usable electricity. This is our not usable electricity, wasted, the foam. You blow it off, whoops, and this is the total value of this. And we'll be looking at this from a geometrical standpoint next week, okay? Here's what the review that we just talked about, okay? We have our resistance, which is our true power. Our reactive, which is our imaginary power, is your foam, if you will, your imaginary beer, all right? And this is your power total, okay? This is the rest of it. This is the actual useful stuff. More importantly, this is what you'll be billed for, okay? All right, especially if you're in a factory. That's the main thing. It's what you're going to be billed for. Residential, they say they don't bill for this, but all right. And then we talk about the quality factor of our Q, okay? And how good of a, so we talked about this. Well, how good is the resistance? Like, okay, so we have this much resistance in the windings. Is that good or bad? Well, it depends on what the Q you're looking for is. So let's talk about what that means. The quality of an inductor is defines how close it comes to an ideal inductor. Okay, the ideal inductor has zero resistance winding, so it dissipates no real power. So when you're using a program in the computer like multisim, or you're doing something mathematically like we just did with X of L, we're assuming no resistance for the windings. But in the real world, that's not going to happen. All right, so the inductor of Q can be found by using the reactance to real power, which is a little confusing at this point, or we can just do how we're going to do it in lab. We have the X of L and the resistance windings over here. This will tell you your Q value, okay? So here's an example. Let's say we have X of L of an inductor at 350, and that is divided by 5.5. Let's go ahead and run that and see what value we come up with. So we'll move this over to here. So we'll take 350 divided by 5.5. That comes out to be a Q of 63.6, okay? All right, 63.6 is where we're at. All right, is that good or bad? Well, it depends, right? That depends. Some people would say that's really bad, but you'll notice here that if I increase my frequency, this would increase my X of L, but my RW would not change. All right, so my Q factor will get a lot less, right? Okay, so let's do that experiment here. Okay, so let's say I increase my frequency and my X of L skyrockets to, we'll just go much higher. We'll say 3,500. All right, will still be divided by 5.5. Now my Q is 636. Okay, all right. So note that the Q is a ratio and does not have a unit power. All right. And so I think what we're going to do is we're just going to go ahead and end the lecture here. I've been really beating you guys up with a lot of knowledge. And so this is a good place to start. The lab has already been filmed and it will be up here. So once you've completed this lecture, you can hop right to lab. You can pause this lecture as many times as you need. You can go back and listen to it again if you're just one of those people who likes to be driven crazy. So anyway, thank you guys very much. This is our first lecture online. I know this is difficult. I know it's going to be frustrating and I know it's going to be hard, but please know that I'm here for you. And if you have any questions, please let me know right away. All right. Thank you guys very much.